In 2019, Google's Sycamore processor shocked the world by completing a calculation in 200 seconds that would have taken a classical supercomputer thousands of years. At the time, it sounded impossible. Then came Willow, a quantum chip so powerful that a task it finished in under 5 minutes would take the fastest classical supercomputer 10 septillion years. That is not just a big number. It is a number so enormous that it pushes the mind beyond normal reality. And that is where the mystery begins. Because if a machine sitting inside our universe performs a computation that seems too large for our universe to physically contain, where is the extra power coming from? Some physicists believe the answer is disturbing. Quantum computers may not just calculate inside one universe. They may need other universes to work at all. Not as fantasy, not as science fiction, but as one of the most serious interpretations of quantum mechanics. And if that is true, then every quantum chip may be more than a computer. It may be a machine that touches the hidden architecture of the multiverse. For centuries, physics made the universe feel predictable. Planets moved according to laws. Objects had positions. Causes created effects. If you knew enough information, you could calculate what would happen next. That was the classical world, the world of Newton. Motion, gravity, and common sense. It worked beautifully for apples, planets, engines, and buildings. But when scientists looked deeper down into atoms and particles, common sense collapsed. At the quantum level, particles do not behave like tiny balls. They behave like possibilities. An electron can exist in more than one state at once. A photon can travel as if it explores several paths simultaneously. A particle can remain uncertain until it is measured. And two particles can become entangled so deeply that they act like one system even across distance. This is where the old picture of reality breaks. The Copenhagen interpretation says quantum systems exist as probability waves until measurement forces one outcome to appear. In this view, the other possibilities were never separate realities. They were possibilities inside the mathematics. But the many worlds interpretation says something much stranger. It says those other possibilities do not disappear. They happen. Every possible quantum outcome becomes real in a separate branch of reality. When a particle could go left or right, it goes left in one universe and right in another. When a measurement has several possible results, every result occurs somewhere. That idea sounds outrageous until you realize quantum computers seem to behave as if many possibilities are physically available to them. They do not test one answer at a time like classical machines. They manipulate entire clouds of possibility at once. And that raises a frightening question. Are quantum computers powerful because they are fast, or because they are not working alone? To understand why parallel universes enter the conversation, we have to return to one of the strangest experiments in science, the double-slit experiment. Fire a single photon at a barrier with two slits, and common sense says it should pass through one slit or the other like a tiny bullet. But that is not what happens. The photon creates an interference pattern as if it behaved like a wave passing through both slits at once. Even when photons are fired one by one, the pattern still builds over time. It is as if each photon is interfering with something invisible. Now make the experiment even stranger. Add more slits. You might expect the pattern simply to become brighter or more spread out. But instead, certain places that were bright can become dark. Adding more possible paths can remove light from places where light existed before. Something invisible is shaping the result. This is where David Deutsch's interpretation becomes so unsettling. He argued that when we see interference, we may be seeing evidence that our particle is interacting with counterparts in other branches of reality. Not ghosts, not magic, but real physical counterparts that we cannot directly observe, whose effects appear through interference. In simple terms, the photon we see may not be the only photon involved. There may be shadow versions moving through other possible paths and influencing the outcome in our world. If that is true for photons, it is true for all quantum particles. And if it is true for quantum particles, then the physical world around us may be surrounded by countless parallel branches, invisible but mathematically active. Quantum computers take this weirdness and turn it into engineering. They do not avoid superposition. They use it. They do not fear interference. They control it. They build calculations from the same strange behavior that makes one photon act like it traveled through many paths. That is why the double-slit experiment matters. It is not just a classroom mystery. It may be the first clue that quantum computation is powered by realities we cannot see. A classical computer solves problems step by step. It stores information in bits, zeros and ones, and moves through instructions one after another, even if it does so extremely fast. But a quantum computer uses qubits. A qubit can exist as a combination of 0 and 1 at the same time. Add more qubits, and the possible states multiply exponentially. This is where the numbers become almost absurd. A 50-qubit system already requires an enormous amount of classical memory to simulate. Around 300 qubits would require more classical bits than there are atoms in the observable universe. That is not a poetic exaggeration. That is the scale of the mathematics. So when a quantum computer performs certain calculations, it is operating in a space so large that no classical machine inside our universe could represent it completely. So where does the computation happen? The standard answer is that it happens inside the wave function. The quantum state encodes the possibilities, and the machine manipulates probability amplitudes until the right answer becomes more likely. That answer is accepted by many physicists and does not require parallel universes. But the many-worlds answer is far more dramatic. It says the wave function is not just a mathematical tool. It is physically real. The different possibilities are real branches of the universe. And when a quantum computer runs a calculation, those branches interact through interference. Each branch carries part of the computation.